Greetings, Earth and Space explorers. Welcome to Doc Waller's Earth and Space Report for Friday, April 23, 2023, the first report in our fourth year of monthly gatherings. I'm your host, Bill Waller, an astronomer, science educator, and communicator, coming to you on a cloudy spring evening in my hometown of Rockport, Massachusetts. These Earth and Space reports are intended to engage and inform people like you who are curious about Earth as a planet, who care about our life-sustaining environments, and who wonder about the greater cosmos and all that it contains. Video recordings of these reports are archived on the Earth and Space Reports YouTube channel. They are also in regular rotation on the 1623 Studios Community Access Cable Television channel. I'm grateful for the continuing interest and support shown by Rockport educators and students, Cape Ann cultural colleagues, cohorts of the Gloucester Area Astronomy Club, sundry Earth and space scientists and communicators, far-flung friends, family, and other curious folk. Thank you for your active participation and encouragements. This evening, we will be introduced to the adventure of imaging the night sky from myriad locales, including tropical beaches, northern lakes and forests, and even vineyards. Our host is Tony Weinbeck, a PhD candidate soon to join the University of Wyoming. Tony earned his bachelor's degree at MIT and his master's degree at Tufts University. While at Tufts, he worked with yours truly, researching the infrared emission from star-forming activity in the Triangulum galaxy as imaged by the Spitzer Space Telescope. For the past decade, he has been teaching at Normandale Community College in the Twin Cities while honing his skills in astrophotography. He has photographed the night sky from the western beaches of Hawaii to the eastern shores of Puerto Rico and the northernmost tip of Minnesota. Tony is also a trained sommelier, a certified wine snob, and his worlds collided when he observed the great North American eclipse of 2017 from the Vineyards in southern Oregon. He has recently begun research with a science team with the James Webb Space Telescope and is living the dream of cosmic questing. So welcome, Tony. The Zoom platform is all yours.
Thank you so much for the great intro, Bill. And I just have to say that in addition to doing research with you, I was also, I had the great fortune of being your TA in basically the intro astronomy courses there. And I think even more than the courses and the research we did together, I learned so much from you from actually being in the classroom. And I'd say my now current lecture and classroom style is directly attributable to you. So thank you again for spurring my interest and my passion for this. Wow. And we're all lucky to have you here leading these as well.
Okay, good.
So I'm going to go ahead and share my screen here. Let me make sure I know how to do this again. And I will pull up our, let's see, a little bit more enlarged. But okay, so back to kind of where we're at here before we went off the rails. So partly what I want to talk about here today is astrophotography just as a whole, some of the technical aspects of astrophotography. I had originally intended to show a whole lot of pretty pictures of the night sky from the Vineyards for a reason I'll get to in a second here. I've kind of audibled that, and instead we're going to be spending the first, I'd say about 2/3 of the time talking about just kind of the technical aspects of astrophotography, partly how, for example, DSLR cameras work, and I'm going to focus on DSLR astrophotography. But I'm also going to talk about and discuss exactly what happens in the post-processing for, once you've already taken your images, how you convert that from raw into the final form, the pretty stuff that we see on Instagram, Facebook, whatever. Mm-hmm. And then I will go through, I didn't want this to be entirely just a slideshow of pretty pictures, but I have to have some here, of course. The audible that I've done is because since Bill and I arranged this talk a number of months ago, and between then and now, I've begun working with the FANGS group, PHANGS. You can Google it, but they specialize in observing faraway galaxies, and specifically with the James Webb is the data that I'm working with now. So the addition is that I will instead be also talking about data that we got from the James Webb that I'm currently processing, which I am super excited about. So let's just go ahead and go through kind of the hardware and the main calibration aspects of the sensor technology. And the first question is, what is a camera? And I do have to point out, this is not the only slide in my talk that will include a picture of both a bear and a camera. But so the question here is, what is a camera? Or more specifically, what are the three components that are both sufficient and necessary to classify something as a camera? So, number one, you need a lens or some contraption that focuses light. Number two, you need a shutter, the thing that either allows the light to pass through or prevents the light from going through. And you need a sensor to actually sense that light and to be able to make your images. Now, not only that, but one could argue very reasonably that in addition to these three components, you need a fourth item, which is it directly relates to the lens, but we call that the aperture. And the aperture right here is one additional component that basically allows you to either constrict the light or that allows you to collect a maximum amount of light. And we'll go into what each of these four items does for you in the photographing process. And again, I want to be clear that I'm focusing this talk on not like telescope photography, not photography with a professional camera, a CCD lens, mainly just a lens, consumer grade electronics, camera body, and then all the built-in software here. So let's again go through each of these four items here and describe how you can change them and what effect that has on your final images. So first thing, the lens. Arguably the most important item when you're making your composition or you're trying to frame your picture is what focal length to use. And the biggest difference between each of these series of lenses here, which are all very, very expensive lenses, by the way, it's a Canon L series. The biggest difference is the focal length, which is essentially how long or how short the lens is. Now, each of these are very complicated. They have anywhere from 10 to upwards of sometimes 20 individual lens elements. In the past, if you think about the telescope that Galileo had used, it was literally just a lens there, a lens there. And the focal length was roughly just the length of that entire telescope. Now with this complex packaging of lenses, it's no longer, you can't directly tell the focal length just by how long the lens is. But the reason why the lens matters is that it essentially determines your field of view. The longer that focal length, the more zoomed in you get. And these ratings here are more relevant for again, consumer grade electronics, for standard lenses that you just go in the shop and buy. You can get some much, much longer lenses if you, go to a specialty store or if you, purchase a telescope, for example. But this is roughly what in what I consider like landscape astrophotography. These are the three classifications, and just to kind of get a feel for what those three different things do for you. We have, let me zoom back out a tad. We have all the way from 14 millimeters, which captures essentially it's about a 90-degree field, a little bit more than that, maybe 120-degree field. And you can more or less capture the entire bright lanes of the Milky Way, down to, obviously, if you were at 100, 130 millimeters, 200 millimeters, you're zooming in on smaller and smaller regions, smaller than, for example, constellations. And once you get to about 1,000 millimeters, which is roughly the focal length of my backyard telescope, now you're zooming in on what we call deep sky objects, or things that typically aren't visible to the naked eye at that point. So the focal length, again, it determines your field of view. The longer the focal length, more zoomed in you're going to be. So in addition, lenses also include, or modern day lenses include, the ability to change how much light passes through. And we call that changing the aperture. So for example, a lens with a very large aperture, you'll see right here. And I'm not going to explain exactly what those numbers correspond with. Feel free to Google it. It's actually somewhat complicated. But the long and the short of it is that the bigger the number, the more constricted the light will be as it passes through that lens. Now, if you think about it, in normal, like everyday photography, the reason why you would use a lens like that is, let's say it's a very, very bright sunny day. There's so much light that if you just like hit the shutter and undo the shutter, the sensor will be completely saturated with light because there's just way too much light you're dealing with. So that's why you would choose to go with this aperture in very high light conditions. You want to block out most of that light. There's one more thing that does too. For astrophotography, you're at exactly the other end there. you have a minimal amount of light. And that's what makes astrophotography so technically challenging. You're trying to capture the maximum resolution with a minimum amount of light. And this number here, typically you don't see lenses that go much beyond that. I've seen a f over 1.2 or f over 1.0, but they're very rare. But you want to take the maximum amount of light in, but that introduces slight challenges. So for very wide aperture, which is what I'm talking about here, this is much better for low light or close-up portraiture, which, by the way, I did Google that, and that is in fact a word, portraiture. It's the act of composing portraits. And the reason why that's important is that if you have, let's say, like a happy, smiling kid here, and there's a background like a park behind him, you don't want your photo to be so busy with the background that you capture that you don't see that happy, smiling kid. So if you open the lens wide up, what's going to happen is that at the point of the sensor, as long as you're in focus, the kid will be perfectly focused, but the background is going to be more diffuse. It's going to be more blurry. And that's specifically because the focal plane is different depending on how near to the camera you are. And again, there's a lot more behind this, but if you open the lens wide up, you can focus on a very narrow part of the image, and everything else in the foreground and the background is going to be diffuse. Now, for a very small aperture, that's no longer an issue. Both the foreground and the background are in focus at the same time, but at the expense of you allow a lot less light through. Mm-hmm. Now, this is almost exclusively what we use for astrophotography, both because we're dealing with low light and because we only care about the background. We can focus on the background and nothing is between us other than atmosphere. So that is the aperture here. By the way, I will try to kind of monitor the chat. If you have questions, please feel free to shout them out there. Mm-hmm. Okay, so the second thing, the third thing, focal length, aperture, shutter speed is the third parameter that one can change when taking images. And I think it's somewhat obvious here where you want to fall when you're doing astrophotography. If we're dealing with very low light levels, the obvious thing to do is take a much longer exposure to compensate for that. Now, there's a couple caveats here. Maybe the more obvious one, having to deal with Earth's spin and rotation, we'll get back to in a second. But one of the more technical aspects of this, which is what the specific reason why we choose to do a longer exposure, is not just to collect more light, but it has to do with getting a higher signal or higher signal to noise specifically. So this will be the most technical slide on the presentation here. So don't worry too much if it is slightly gibberish, but for any sort of science, not just for astronomy, for any sort of science, if you want to trust your results, that means that you want to have the highest signal to noise, or in other words, the smallest error bars for your measurements. Those are in words synonymous there. And for any sort of a light exposure, what's literally happening at an atomic level is individual photons are entering that lens system, they're passing through, and they're interacting with the electronics on the sensor. So every single photon that hits the sensor is what we call a single count or a single measurement. And now for any sort of image, of course, we're not just detecting a few photons, we're detecting hundreds or thousands of them for any exposure. But the number of photons that we collect is the same thing as what we call our signal, n. So if you're collecting n photons, now let's say we do that same exposure over and over and over, are you guaranteed to get exactly the same number of photons in each pixel? No. The number of photons we collect in one exposure is probably going to be very similar to the number of photons in the next one and the next one. We're imaging the same thing. But there is, among other things, there is quantum uncertainty about the number of photons we collect. Every time each pixel is going to get a very similar signal, but it might be a little bit different. It might be 1% higher in the next exposure. That single pixel might be very slightly lower in the next. And this is essentially the error bars of our measurements. If we measure a given signal n, how likely is our next measurement going to be within that range? And the error bars, or the predicted deviations from measurement to measurement, is the square root of n. There's a lot of complicated probability here, but this is what we call Poisson statistics. That if you have a measurement of n, your error bars of that measurement will always be the square root of n. So in taking this ratio here, which is the thing that we want, how small our error bars compare with our overall measurement, you just literally take the ratio n over the square root of n is just the square root of n. And what that means in practice is that in order to double your signal to noise, which again, that's effectively you're doubling your clarity of your image, is one way to say it. If you want to double the clarity of your image, you need to take 4 times as much data. If I want to triple my signal to noise, I need to take 9 times as much, because the square root of 9, the square root of n, is 3 in that case. So it doesn't scale linearly. You can't just double the length of exposure to double the signal to noise. It does go with this root n factor, which this is one of the reasons why getting very, very long exposures to maximize your data is extremely difficult, because you have to quadruple your exposure time for every doubling factor that you get. So just for example, here is the same source set up, and correct me if I'm wrong, that sure looks like the Andromeda galaxies to me. This is taken from, let's see, so I have somewhere the credit on there, but this is, I believe, the Andromeda galaxy here.
Yes.
And going from 1 minute, sorry, Bill, is that right?
Yes.
It has to be, yeah. My only other guess is M63, well, anyway. But so what we're seeing here is very short exposures. If you were to zoom in very closely, there is a significant amount of noise. You can barely make out those little dark bands on the outside there. As we increase that exposure by roughly a signal to noise factor of 2, very clearly you can start to see more structure. Same thing, another signal to noise factor of about 2. Now those bands are clearly visible both the near side and the far side. And then going up to an hour, this is where the full clarity of this becomes at least clear. But what's happening again, every doubling of exposure time, sorry, every quadrupling of exposure time, you're doubling the signal to noise. There's an issue with this though. Actually, one more thing before that. This is a really cool animation of this. So on the left, you're going to see the individual frames. On the right, so I'll get to what this is here in a moment, but on the right, we're going to make a composite image by taking a whole lot of individual frames, 880 frames. And I don't take credit for this. This is done by a Reddit user called Helmi Helmuto, which is now my favorite Reddit username. But he's very German from Berlin. He or she is very German from Berlin. Anyway, so I'm just going to play this here and just watch how the composite image increases in clarity and how the signal to noise ratio increases with the number of frames. I'll play it a couple times. Very, very clear. Other direction, grainy. Grainy, grainy, clear, clear, clear. Back to that. Play one more. But yeah, so this is literally the effect of taking longer and longer exposures by combining individual sub-exposures, is what we say. Okay. Now, the one trade back of that is you can't just set your camera up on a tripod and then say, hey, expose for 3 hours, because the obvious effect there is that as the Earth rotates, the stars in the sky or the moon or whatever it is you're looking at is going to move. So we have a conundrum here. Do we want to take a really long exposure and maximize our signal to noise, or do we want to take a really short exposure and minimize that rotation? And just to get some sort of a idea for what this looks like here, this is what a 30-second exposure looks like with these settings here. I'm not going to go in detail about that, but very clearly, even with 30 seconds, you can start to see the star trails here. As you lessen that exposure, we're seeing shorter and shorter star trails, and this is from Roger Clark. He's actually calculating exactly what the pixel trail is. So down to about 10 seconds, maybe 8 seconds, the stars now finally begin to start looking like points, but that's at the expense of much higher noise. Now, here is the kicker. What we do when taking a very long exposure, if you're taking longer than, say, 15, 20-second exposures, what you can do is put your camera on a star tracker. So this is kind of the cheat code out of this whole issue in the first place. So this is This is a star tracker, and the way it works, let's say this is north. You put this on your tripod. If this is north, you attach your camera up here and you hit go. and it now very slowly begins rotating exactly at the same speed the sky does, fixed on the North Star. And I'll shift it over here. So let's say the North Star is that direction. Your camera is going to be rotating at exactly the same speed as the sky. So in this case, I've taken 5-minute exposures, and there's literally less than 2 pixel deviation as long as I align it right. So you can just open your shutter, let the camera go for long periods of time. And as long as you align it properly, you can, in fact, get very long exposures without any star trails. Now, the one downside of this is it does take quite a while to align to get that long exposure. So there is some happy medium there. But there are occasions for sure where, oh, by the way, the one other thing I want to mention here, based on what we see here, the this rule, what it's talking about is the rule of thumb that at least traditionally used to be correct was that if you wanted the longest exposure you can make without seeing significant star trails, basically what you do is you take the number 500 and divide it by your focal length. In this case, the camera that was used to make this composite is a 35 millimeter lens. So in this case here, if you take 500 divided by 35, what is it? That's about 14 or so. Sounds right. Yeah. So in this case here, the maximum length exposure should be about 14 seconds or so. We look down, we see a little bit of trailing. This is if you're, if you zoomed in on the image. Now, when you go below 500, modern day electronics actually are good enough that you can still substantially see that, even if you're using the rule of 500. So the way that many astrophotographers do it now is it's about the rule of, I'd say the rule of 400 or the rule of 350. You take about, and we'll just say 350 here. You take 350 and divide it by your focal length. That's the exposure length where you shouldn't see any trailing. And that's what this image, this frame is showing there. So if I was using this 35 millimeter lens, I happen to know that my sensor on my camera is sensitive down to about the rule of 350. So I would say a maximum about 10-second exposure here. So again, 350 divided by 35 is just 10. So that's where we get that. So anyway, if you're out in the field, that's an easy way to know, given your focal length, roughly how long exposures that you should be taking before you have to start worrying about that. Now, as I was saying, though, there are in fact situations where you do want to let the star trails play out. And it gives a really cool artistic effect that if you're doing astrophysics, trying to get very high resolution images of, say, galaxies, this is something you want to avoid at all costs. But if we're doing it for astrophotography, the artistic side is a little bit fun. So I am going to actually show exactly how I composed this exact image here. I think I'm going to have to stop sharing for one moment and flip screens. All right, can I get confirmation that you can all see my screen?
Yeah, it's just one thing. Well, I see what you're doing.
So, can you see a screen where I have a whole lot of images on the left side there?
Yes.
Okay. So I took a whole series of photos when I was in the Badlands last October, and this was my campsite there. Now, just to note, this was at like midnight. The reason why you can very clearly see the formations is that it was a full moon, which obviously if the full moon's out, you're not going to be getting great deep sky images, but it is great for landscape images. And specifically what I did is I set the camera up near my tent. I have my dog with me, by the way. But I set the camera up there and just took a whole series of minute-long exposures. And if you can tell by the size of the number of images I have here, this went on for about 3 hours. So I'm going to start playing this and I'll describe what's happening as you see it. So I'm going to go through all 300 or so images. And now notice what's happening here in the sky. It's processing image by image by image. And what it's doing is for each set of 2 images, it's going to keep the maximum pixel at each point. In other words, if you have 2 images that the pixel number 1,1 is fairly low in the first image, the pixel number 1,1 is very bright in the second, it's going to discard the lower value and keep the brighter value there. It does that for all the pixels throughout the entire picture. It keeps the maximum value of the entire set of images, and now you see something fun happening down there. So if I were to zoom, let's see, yeah, 164 images processed. If I were to zoom in down here, what's happening is that not only are we seeing star trails, but we're seeing towards the end of the night, when I have my camera, and I had a little light attached to my dog at one point, this is literally my headlamp as I'm coming to the tent to go to sleep that night. So you can literally see those last couple minutes where I was just finally getting ready for bed at 3 a.m. or whatever. But does that algorithm make sense? If you have a whole series of images, you want to take the maximum pixel across that entire set of all images, and you're only keeping the brightest, which very clearly delineates any sort of star motion and also invert flashlight motion here. Cool. Okay. So, and this is the resultant image there, which I thought was kind of neat. I intentionally framed it so that the North Star was directly above my tent there. And then the last thing, again, like I'd mentioned, this is all just entirely lit up by the moon, which is kind of a cool effect. Okay, so I want to talk a little bit here about sensor technology. And this is really the last major thing that you can adjust on a camera while taking exposure. And the long and the short of it is that for anyone who's ever played with a DSLR camera, there is what we call the ISO, which some people will say the brightness of the image, or you can maybe somewhat and falsely think of it as how sensitive that sensor is to light. Now, that's not actually correct, but the effect of that is, though, thinking that way, is that as you turn the ISO up, you're making the resultant image look brighter on the screen or on the computer. Now, the difference is, though, turning that ISO up does not collect more photons. It does not, in fact, collect a higher signal. Not only are you multiplying that number of photons, you're also multiplying any inherent noise in the sensor. So the tendency for a lot of beginning astrophotographers is they want to just ramp up that ISO. The problem is, for most cameras, there are some exceptions, but for most cameras, as you're ramping up that ISO, you're actually increasing that noise at a nonlinear rate, or ramping up that ISO too far will actually create a noisier image in the end. And this is just a little bit of background for that. I'm not going to go much into detail, but the technical reason for this is that there's two separate amplifications that occur during the exposure. The first is that you have in the sensor, so you open the shutter, you collect a bunch of photons, you close the shutter. At that point, you need to read the signal, which is read the number of photons that were collected in each little square, each little pixel on your sensor. And so the technical process of doing that is you basically like open the gate, you let the photons out. Now, those photons actually, slightly more technically, the photons interacted with the material in the sensor, and it created an electrical signal. So a bunch of electrons is what you capture, basically. You open the gates, you let the electrons out, and you measure that initial voltage based on the electrons leaving the sensor. That's an analog amplification. You're not doing anything digital. You're literally just multiplying the voltage that's inherent on the sensor there. The next thing that we do is we do a digital amplification to go from a raw analog signal to a final bit by bit by bit digital signal. Mm-hmm. Now, just again, slightly more on the technical side, if you have a very low ISO, what's happening is that this upstream read noise, if again, for a very low ISO value, this upstream read noise or the analog amplification that we did right initially, this noise is going to dominate there. So if you go too low on the ISO value, you're going to have noise caused by this analog amplification. If you ramp up the ISO, the reason why that's not a good idea is that this noise now begins to dominate the image. So you need to kind of find some happy valley. And there is a resource on the web for at least Canon, Nikon, and Sony cameras. Here's the link on the bottom. But there's a resource where you can find essentially the best ISO that is that happy medium, that's the best analog and digital amplification. And clearly there is some, I don't want to go into details again on this graph, but the ISO between about 800 and 1600 is, for my specific camera, is the ideal one where you're minimizing the overall noise, and also you're not losing any dynamic range. You're not cutting off the highs or the lows. So again, for those of you who are interested, I encourage you to follow this link. I can post it in the chat later. All right, so I want to go into a little bit of post-processing here, and I am going to keep this a little bit, I might go through a little bit more quickly so we have time to show some pictures at the end. But this is what, and the nice thing is this is not true just for astrophotography. This is true for everything, including the pipeline for the James Webb. There's a couple basic steps. And the reason why we have the same steps for everything from $100 camera to $1 billion camera is that you're correcting for the same types of artifacts or the same types of mistakes in your images. And I don't want to say it's a mistake because there's no way around them. The thing that we have to do is just know how to correct for them. So the first thing that we want to do is when we're talking about that camera technology, remember that we're dealing with an electronic sensor. Those photons, like I said, get converted to an electric signal at each individual pixel. And for anyone who knows basically how current works in a circuit, the only way to make those electrons flow through that circuit is to impart even the smallest voltage onto it. Or in other words, those electrons that are essentially measuring the signal on the sensor, those electrons can only leave that sensor if you apply a voltage to get them off that sensor. And so it's necessary in order to actually make your reading to impart a bias voltage, is what we call that. It's a voltage, it's a voltage that we call it the bias signal. And if we didn't have that non-zero voltage at the beginning, we would not be able to get off those electrons and make our image at all. So this is a kind of example of in the middle is an uncorrected frame, and this has been exaggerated here. But you can very clearly see that there is a horizontal striping here and a vertical striping. And that corresponds with literally the XY pixel grid on your sensor. You see that for whatever reason, there are grids that will be a little bit darker. There are columns that will be a little darker, columns that will be a little bit lighter. Same thing in the horizontal direction. Now, the nice thing is that cameras, you can determine exactly what this bias voltage is. So what we're seeing here is the little bit of difference between readings for each row and each column. That's literally what that the voltage bias, I don't know why I keep saying voltage, the voltage bias is. But what we can do, the way to correct for this is put the lens cap on your camera. Turn the shutter speed down to the very lowest that you can possibly take. In this camera, it happens to be 1/8,000th of a second, which is unreal. So basically, we want to capture a picture with nothing but that electronic noise. And so by capturing a very, very short duration exposure, the reading that you get out is strictly just whatever that tiny amount of bias voltage that we put into it is. So the reason why we know this is the proper correction for this image is that we've taken basically a control reading with everything else except for that bias voltage there. We subtract it, and you get a much clearer image. And again, this has been exaggerated to kind of show this effect in practice. But by the way, 18 points for anyone who knows what this is there. Throw it in the chat if you want. Another 3 points if you know the Messier number. Okay, so the next thing is step 2. We've subtracted that bias voltage, or that baseline voltage that we can't avoid. The next thing is that for long exposures, and again, if we're using that star tracker even longer, as you sit there with a sensor that is collecting more and more signal, there is going to be some what we call Johnson-Nyquist noise, or more commonly known as thermal noise. Now, we know that for any sort of electronic device, the electrons are going to have, basically there is some impurities in the conducting path, and the electrons are, the current is not always going to be perfectly constant. There is a slight bit of deviation from it, and the hotter the conducting material gets, the more deviation there is. So if we sit there with our sensor open, or sorry, our shutter open, capturing more and more signal, literally the sensor heats up. And most good cameras have an actual sensor temperature gauge. But you can tell that your sensor is 20 degrees above ambient or so. And what that results in is there is this very significant deviation because the sensor is heating up, causing more electronic noise. Now, it's a little bit tough in this image to see it, but if we kind of exaggerate that, you can see that even if you have the lens cap on, which is how these frames were taken, even if you have the lens cap on, for longer and longer exposures, you're going to see more and more non-zero signal. And this Canon 1000D here is particularly noisy, that for sensors that are warming up, they're heating up, you're going to have some noise inherent to that sensor just because it's warming up during exposure. So the way that we control for this is that we put the lens cap on, we take all the settings to exactly what we want for our final exposure when we actually have lens cap off. But what we want now is when we put the lens cap on, if you let your camera go for, say, 30 seconds, if that's what you're going to be doing, or 5 minutes or whatever, now what we can read is what is the image that results from no actual signal? What are our hot pixels? So you're measuring, back to this here, you can see there's a couple hot pixels there. And when we exaggerate it, it's not just a couple, there's a whole lot. So we want to eliminate this random thermal noise from each pixel. And so literally we just take a series of exposures where you leave your lens cap on for 5 minutes or whatever it is, whatever the proper time is. And then whatever that thermal signal is, we're going to subtract that from our final image too. So you've gotten rid of the dead pixels and you've gotten rid of the deviation from the sensor voltage. So that basically takes care of our electronic noise. The next part is, what is the optical imperfections of the system? So let's say, for example, you have a dust smear on your lens, or you have a little speck of something on your sensor. We can actually even correct for these things. And here's an example of before and after when we're correcting for the optical imperfections. And I'll come back to exactly what that means here in a second. But what we're doing here is we're going to take an image. Well, okay, so let's just talk about this here. One of the most significant differences is towards the edge of the image. You see a very definite darkening. This is called vignetting. And this is just simply for any lens, particularly the very high aperture lens, the ones that have a very large area of light collection. The edge of your image is inherently going to be dimmer than the center of your image. And what we do in this case here is you take your camera and you take the lens cap off and you take a whole series of images of a very bright source. Now I happen to have a lamp next to me here. And what I could literally do is just take a whole series of images close up of the lamp. And that will show you what optical imperfections are in your image. With a telescope, what you can do is you can take basically a white t-shirt and fasten that white t-shirt onto the end of the telescope and point it at like a daytime sky. And again, any imperfection in that optical train is going to come up as a blur in this image. So this is an example of what we call a flat field. These little dots here are grains that are somewhere near the sensor, like dust grains. You can see some smears. Those are probably being caused by the lens itself. And the vignetting, which is something that's inherent to any sort of optical train. So once we take these blank images of what should be a flat source, that's why we call it a flat field. If you take an image that should just be pure white and then subtract that, or in fact, we don't subtract it, we actually divide by that. I won't get into details, but we divide by that flat frame. This we see what appears to be a perfectly smooth image without any systematic offsets from the optical imperfections. And any dust grains or anything that may have been in here previously have now been smoothed out as well. So this is basically, yes, go ahead.
Mario has a question. Mario Mata.
Okay. Please go ahead.
I don't want to interrupt you. But when you're talking about the bias frames, is that as important for CMOS as it is for CCD?
Yes, and I would say probably even more so, because
Really?
CCDs you can typically, or at least the modern ones, are almost all cooled. So you can cool them down to -20, -30 Celsius. Relatively few CMOS chips are like that, and I think they do have inherently more noise than the CCDs.
Well, I'm using Astro cameras, and I find that the CMOSs in the Astro cameras are definitely less noisy than the CCD. Now, I know it's different for cameras, but
Yeah.
I stopped bias subtracting with the CMOS because I didn't notice any significant signal. But I didn't want to interrupt you. Go ahead.
Okay. Yeah, and I will say that some cameras are actually much more inherently better. The modern cameras that are coming out now, you essentially don't even need to take darks anymore. The longer exposure, it's just the sensor technology has increased. So I might also, it might also have to do with how old or how new those cameras are too. Okay, so the last thing I want to talk about before we go on to some of those pretty pictures here is By the way, I saw one other question in the chat. It was how many bias frames should one take? And that's a great question, and there's no right answer there. What I do is I usually go for about 40 bias frames. And beyond that, you have, and I'll explain how to combine those here shortly, but beyond 40, it's the law of diminishing returns. Just taking one bias frame, you're going to have the issue of the measurement error, that Poisson statistics, even for no signal. The more frames you get, and if you, for example, average them, the more you can be certain that, to the best of your ability, you're correcting for the proper amount of bias or darks. At 40, that's fairly easy to take for biases. For darks, I usually like to take around, I don't know, between 10 and 20, because those are inherently longer to take. So let's see. How does this all change if you're using film? I am not sure if I'm qualified to answer that. Oh man. Let's chat about that in the post questions here. As others of you might actually have better answers than I. Okay, so let's go back to slightly more what I was talking about here. And this comes from, so our discussion of how many you need to take is relevant because the way that we do that in astrophotography is we stack images. And we take a whole series of the same image. And this also works for daytime photography too, by the way. So we take a whole series of the exact same image. They're not going to be perfectly the same pixel by pixel. But if what we do, after you collect that entire series of images, if you take the median value or the average, we prefer to use the median because it rejects outliers better. But if we take the median value of each pixel, you're essentially saying that we're averaging all these images so that if some have a slightly brighter pixel at that spot, if some have a slightly dimmer pixel, it doesn't matter because all of those get averaged out. And you end up increasing your signal of noise exactly as if you just took one very long exposure. And in the result here, as it's displayed, you can see generally that fuzzy background tends to go away and it smooths out, and you get sharper detail, higher contrast. This image I think is really cool. Someone took a close-up of just some Lego figurines. It was on a tripod, same exact images, so no proper motion between. And you can very clearly see how the detail is increased by just stacking even 30 images there. And you literally have a noisier image here because it's just a shorter exposure. Now, these are individual exposures, but effectively, like I said, by stacking them and proper using the right algorithms, you do in fact end up with the same equivalent of a longer exposure of that same source. And it works exactly the same for astrophotography. The more images we take, the more we can stack, the better signal we get. And remember, the reason that we have to stack images in many cases is that literally the sky turns, so you do have a maximum exposure length that you can have in the first place. Okay, very briefly, once you've done all that, now it's time for the post-processing. And this, I feel a little bit kind of dirty having this be a super shortened slide, literally a single slide that I'm just going to gloss over, because this is by far what takes the longest in any sort of production of an image. I might take an hour exposure, but typically for my final exposures, I've done over 40 hours of post-processing for that single image. In many cases, you're taking separate frames, you're using masks and whatnot. Long story short, though, what post-processing does, number one, it calibrates all of the exposures like we just talked about. We've taken the bias frames, the dark frames, the flat frames. Now we have to, in our software, in our computer, calibrate them, and that's what the essential post-processing software does. Number two, assuming that we've already calibrated those frames, we can now stack all of them together, or what we more professionally call integrate that exposure. And so we're taking a whole lot of individual images, essentially finding their average that, again, increases that signal of noise. Number three, we can subtract any background, so any inherent, for example, light pollution, or literally just if the sky is darker for whatever reason, you can turn that kind of hazy gray background into a black background, ideally without losing details. Number four, depending on how involved you want to get, we typically, these cameras take color photographs. It's actually, there's literally 3 different colors of pixels in here, and that's I'm not doing that justice either, but what any post-processing software does is it combines the R and the G and the B pixels into one color image. Now, at a slightly more professional level, you'll have a monocam, and use filters. So you might have one set of exposures where you're only collecting green, one you're only collecting red, one you're only collecting, for example, O3 emission, oxygen 3, whatever. So you can calibrate that color so it looks like as most closely related to what you would actually see from a telescope, for example. And the last two things, the stretching of the histogram, basically we just increase the contrast is all that means. And noise removal, that's really kind of a consistent theme throughout this entire process. So again, I feel a little bit dirty in just leaving this as a single slide because it's the vast majority of the work that one does. But for sake of time here, I do want to get to some really pretty pictures. Well, marginally and really pretty pictures. I'll come back to these tip slides at the end. I do have some kind of, suggestions for people getting into astrophotography, people who are intermediate with it. And like I said, I'll come back to that. And people who are maybe pros and hopefully you have a day job as well, literally. But this is a bit of a historical record of my astrophotography. This was literally the first image, the first my attempt at astrophotography from probably the darkest skies that I will ever be at. This was taken from the very western shores of the island of Kauai, the northernmost, most uninhabited of the Hawaiian Islands. And it's literally just like Jupiter was out that night and it was literally casting a shadow on the beach. I had rented some camping gear and I was literally on the western beach just camping out in Hawaii for 3 nights with perfect stars like this. And just for what it's worth, this was taken with a very, very entry-level DSLR. It was my dad's, thank you, Dad. And with what we call a kit lens, or the lens that came with that. In all, we'd be lucky to get like $50 if we resold that on eBay now. So that just shows you, even with really a very entry-level camera, you can get a great photo here. And clearly we can see the dust lanes in the Milky Way, the bright galactic core there, and just, yeah, the incredible amount of stars. Now, with a much, much, much more advanced setup here a couple of years later, this was taken from another fairly dark skies area in southwest Montana. And so this was about a 45-minute exposure. I was using a star tracker for this. And the cool thing was, at the very end of it, one of the very final frames I took, there was a very bright meteor. I didn't happen to see it. I didn't see it until I actually came through the in post-processing. And I did a very small amount of light painting. So some of the exposures, I actually had my flashlight up and I illuminated the foreground. And that's why in a lot of cases, you can actually see some detail in foreground, even if it's completely blackout. Now, I also like that there's actually a very clear reflection of Jupiter in the Jefferson River there too. And by the way, to capture this, I did actually literally wade out into the water and the tripod was sitting on the wet rocks there. So, another example. So this was an example from northern Minnesota. I took on a camping trip with my dog. And all I did was I just set the camera up literally next to my campsite and just left the exposure, or I set a series of exposures for a total of about 2.5 hours, if I recall. The cool thing was, it was the middle of July. These trees aren't red just because we're in Minnesota in July. They were in fact green trees, but the red is the reflection of the campfire that I had right next to me when I was taking this. And as my parents know, I woke up the next morning to this from my tent. And if I'll zoom in a little, I told you that I was not going to have 1 but 2 photos of a bear and a camera there. So that's literally where my camera was. And I just heard rustling. The bear was trying to get in my car and it ended up climbing on top of the car, falling over backwards through it and just scampered away. But I was sitting there with my dog, like 20 meters away, just like watching this whole thing unfold. So it's also a lesson in why not to keep food in your tent if you're in bear country, because you would have been coming straight for the tent instead. All right, moving on here. This is from a recent trip to the Redwoods National Park. I was camping on the beach there, again with my dog. And I set the camera pointing straight south in this case here. And so we're seeing the east to west motion of the stars at about the 35th latitude there. And one thing to note here, not only did I get kind of an annoying helicopter streak, I think is what it was, which I can edit out, but I did happen to capture a couple what I think are pretty dim meteors. And yeah, and so I want to figure out how to keep those. And I haven't finished processing this, by the way. But yeah, so you can kind of see the difference between pointing north for a star trail exposure and pointing south there. Obviously, if you're in Australia, it's the opposite. A few more here. So this is from, again, northern Minnesota. And this was actually a color photograph, but it was just so incredibly dark there that everything just came out in perfectly black and white. And I did have a whole series of these exposures, but I like the contrast of just that. I think it's what is that, a spruce? I'm not sure. From right across the mountains from the Oregon coast. This is just a single exposure here. And so there's the open field in front of me with, you can kind of more or less see Orion here. But it just happened that I had my camera out for about like 2 minutes. And during one of those short exposures when the camera was out, a car happened to drive past and it just illuminated this perfectly green field there. What you can't see is there was kind of a haze there, but that made that car headlamp light just diffuse enough to bring out the green without much detail. So it's one of those kind of freak occurrences that if that car hadn't gone by, I didn't see another car there for the next half hour. So it just happened out there. Badlands in southeast Montana. And I kind of played around with the saturation here, which this is not something you can do in astrophysics. It is something you do in astrophotography. And I thought the result was really cool. You can also kind of make out Orion's belt there. This is the Orion Nebula. And the sky glow there was from the nearest city, which is like 45 miles away, just for what it's worth. Two more of these and then on to the fun ones. This was a photograph from the mountains of the Vineyard in the mountains. So I did say the name of the talk was Astrophotography from the Vineyards. And here's the one token shot there. I've nixed the rest of them. But this was, again, just a perfectly dark night and the Milky Way was there. So I've actually combined a couple different layers of this to bring out the foreground with light painting and the background, which I still need to bring out a little more there. This isn't quite astrophotography here, but I did happen to shoot a T-Rex at one point. This is actually the University of Wyoming campus, and the physics building is directly across the way from the Geology Museum, which has a big T-Rex outside. And this is Jupiter. And I had just long enough break in the sky to actually capture the T-Rex looking at Jupiter there. So I'm going to skip forward a little bit, and I'll come back to those other ones later. But I want to kind of end this with the last bit of what I've been doing recently, which is, again, working with the James Webb Space Telescope, part of the FANGS team. That stands for Physics at High Angular Resolution for Nearby Galaxies, or something like that. It's one of those quirky acronyms, but Bill, I've seen a lot worse from you. So anyway, so these are from the FANGS team, and these are literally just raw James Webb data. So this is M74 or NGC 628. Captured at 7.7 microns. I'm going to zoom into this. This is taken with the MIRCam, but I'm sorry, the MIRI. But what we're seeing here is dust grains that are, we call them polycyclic aromatic hydrocarbons, or PAHs, and they're basically organic molecules. And they tend to be a very good tracer of star formation. And this is something that Bill, you and I had researched in looking at the Triangular Galaxy. But this is just so incredible. Not only do we see these very clear filaments of heavy dust-heavy regions, but we also unexpectedly see these big, huge bubbles and voids. There's another one up here, a couple of them up here. And this is absolutely a problem that we just kind of learned about, or at least learned a lot more of in the last 3 months, because the Webb is very definitely the best instrument to capture these. And the cool thing is we can capture them at multiple different wavelengths to see, are there bubbles in some wavelengths, not in others? Are there stars there, but just not dust? And actually it does preliminarily, if we look at some other wavelengths, it does seem there's plenty of stars here. There's just not a lot of dust. So now we're asking ourselves, why is that? Here's a much prettier professional version of this that they released on their website. It's actually currently my background, but yeah, it's just, it blows me away how incredible the Webb is now. Here's another image. This is the galaxy IC 5332. And it's another one of these spiral galaxies. This is, I believe, it'd be morphological category SA. Bill, you can correct me on that as well. But we see with this, again, this is 11.3 microns. So again, it's tracing out dust in the galaxy. And we see these voids, these bubbles, but it seems like a lot more almost a fractal type of pattern here, which is amazing. The other reason why I want to bring this up to show exactly what I'm working on right now, if you notice, there is definitely some kind of gridding or striping on this. And this is where we're at in the processing. We're now trying to figure out what's the best way to subtract for this, because it seems that the James Webb pipeline isn't properly calibrating for the darks or the bias voltage. So that's an open question as well. And so the final image we should be able to smooth this out properly without that electronic signature there. Two more quick examples. And so these are comparing the last two are comparing two different cameras, the near cam, or the slightly shorter wavelength, and the MIRI, or the mid-infrared camera. And so same galaxy, but here we're seeing mainly stars or stellar emission. Here we're seeing, again, dust emission. And I just say this bar across the center of the galaxy is amazing, but we're seeing more of the rotational dynamics of it with this image there. You can see the leading edge has more dust, and the trailing edge is more of the stellar population. So I think that's really cool. And I'm also pretty blown away by it's essentially kind of a double-lobed spiral arm right there and a double-lobed spiral arm there. We can see it better in other wavelengths. But just the history of star formation on this galaxy must just be unreal. And one other similar image here, this is NGC 4535. Again, stars or near cam images and dust MIRI images. And this is just a classic SC type of galaxy. Is just beautiful. So, and just there's so much more going on in the mid-infrared than the near-infrared. There's so much dust there that, yeah, these are just the beginnings of our questions that we're even starting to answer. So,
good.
I'm going to leave with this slide right here, and I'll post the link into the chat. But this is what I would say the epitome of astrophotography. I think the single best image ever taken. And there is an amazing story about how we've recently been able to sync up exactly this photograph where it was taken with the flight trajectory of Apollo 8. As it went around the Earth started rising. We can actually recreate the exact trajectory of the spacecraft, and we've synced it up with audio of the astronauts, and you can really hear exactly the panic that went into, hey, can we capture this? Oh, we missed it. Oh no, there it is again. We're going to get it right before it went out of view again. So I encourage you all to watch this. I will post that under the chat. It's just kind of, I think, a really cool kind of, it solidifies there's very much the human element in astrophotography, and that panic that all astrophotographers have. Can I capture it? Did I just miss it? So with that, I'm going to check out the chat here. But I have a few more images people want to see. I have the slides for some tips for beginners, advanced, whatnot. But yeah, I think that's where I'm at. So thank you very much, everyone.
Wow, that's great. I certainly needed that review of astrophotography.
Yeah.
And
and obviously, there's a lot more depth you can go into about everything. So
yeah, and so let's open it up for questions. I'm sure there are questions.
I got a question.
Go ahead.
As always, Tony, a great lecture. Thank you very much. I really enjoyed
thank you.
hearing all of that. The question I've got basically is, do they make any digital single lens reflex cameras with like piezoelectrically cooled sensors so that you get your hot pixels eliminated, kind of like what Mario is talking about with his astrophotography cameras, because you can put a piezoelectric chiller and a fan and it'll draw heat away and keep the entire background from heating up. Is that what you were talking about, Mario?
Sorry, I had trouble
Well,
unmuting. Are you asking him or me?
Well, you know, your cameras are piezoelectrically fan cooled, right?
Well, the Astro cameras are thermoelectrically cooled.
Right.
The fan is just to draw out the heat, but it's
Sure,
a
you got to get rid of the
thermoelectric
heat.
cooler.
But I was wondering if they make any DLSRs that have a piezoelectric cooler on their chip.
They
So,
sell aftermarket things for cameras. They're pretty expensive. I mean, if you're going to go that route, just get an Astro camera.
Well, he's talking about a portable DLSR camera that he's taken an expedition. not
But when
a
you try adding a cooler to them, it gets
right,
pretty
right,
expensive.
exactly.
Yeah,
Do they
yeah.
make
And
anything
yeah,
like that?
I agree completely that you can definitely hack it, and I've seen examples of it. But yeah, it's the much more effective way is actually get a cooled CMOS or cooled CCD, Astro specific cam, and then you can get a adapter mount to be able to mount, say, the Canon EF series lenses or the Sony lenses onto that camera body there.
Ah,
Um,
okay. I actually came
so
back
you
from
you
Japan
can
and
turn
stopped
into
in Kauai and saw that night sky. It was
yeah.
spectacularly dark. We saw a boloid, a fireball going across the sky, breaking up from the beach. It was like, oh my God, never saw anything like that. Horizon to horizon.
I saw the same thing just after I took that image. Unfortunately, I almost captured. It was literally a meteor that went the entire length of the Milky Way. As I wish I had made my camera on 30 seconds later.
You almost,
And so the first thing I did, of course, is take another exposure, but it was gone, obviously. But here is my claim to fame with Hawaii, though. Let's see. I was there for an astronomy conference actually when when Kilauea was erupting. And this was again just a few nights before I took that image from Kauai itself. But yeah, this is at nighttime. I think it was a 30-second exposure of basically the current eruption. And then my
how many
friend walked in
miles
front.
away are you at that point from the island?
We were only, we were at Volcanoes National Park at this point, but it was less than 10 miles away, easily.
Wow.
And like we had to be diverted across some of the roads that actively had like lava flowing across it. We were that close. So
Hazards. Wow. Great pictures. Thank you.
yeah. Thank you.
I was wondering if you could show one of your aurora photos, because aurora photography has its own opportunities and challenges.
Absolutely. These were right here. So I captured these last, I believe it was July, when we had the most recent outburst here in Minnesota. And I have a series of other ones. Unfortunately, I found out later on my star tracker wasn't working that night. But actually, it turns out, though, it was my first time ever seeing auroras. But I learned that really to properly get an image of the auroras, because they are so dynamic, that really anything longer than about 15 seconds, it just becomes blurry. And I think this was a 25-second exposure here, and you can even tell like that bright red sprite had actually moved across the sky during that time. Bill, have you ever had the chance to photograph or even see them?
I've had the worst luck with auroras.
Saw a lot of them traveling to Asia on the airplanes, going over Alaska and across the top of the arc. And I saw a day's worth of auroras just looking out the window. It's like, oh, this is getting boring, yawn, yawn. But they're spectacular. They're really absolutely spectacular. And I actually had a chance to go to the observatory in Sydney so I could see the large and small Magellanic Clouds when I was down there in Australia. So nice stuff if you can get it.
There was an aurora this past week that was visible down to Arizona.
Whoa, wow.
And it was a big coronal mass ejection from the sun. And of course it was cloudy
while it was raining here.
Yeah.
I love the sun photos we're getting on at the club.
Yeah. And so I put in the chat, but I would like to just say it on record, is that the International Astronomical Union, its Office of Astronomy Outreach, is hosting its third annual astrophotography competition. And so I encourage Tony and Mario and all the other Gloucester Area Astronomy Club astrophotographers to try their hand at submitting a contender.
Cool. Thank you.
Why don't you send that as an email attachment?
It's in the chat right there.
Oh, okay. Yeah, but I'll lose that when we.
Okay. I promise I'll do that, Mario.
I found that I always open it up and then bookmark it, because I do the same thing if I don't otherwise.
I'll do that and send it.
Yeah, just send it as an email.
But they usually have some sort of theme, and they tend to be something that can be shared worldwide, because this is astronomy for all. And so there's a lot of people doing wonderful things, going through all that you went over, Tony. And it's impressive that people are taking the time and have the patience to do the preparation and the post-processing so that beautiful things come out. For example, Mario Mata's background is from the 2017 solar eclipse, which you saw from the Midwest. Is that right, Mario?
Yep, Marion, Illinois.
And that
Did you take that image there?
Hmm?
Sorry, did you take that image there?
Yes.
That's amazing. Very cool.
He's
Yeah,
good.
and that's a stack of 5 different exposures from inner to outer. So I think the longest was 1/2 second, and the shortest was 1/500th of a second. It was stacked.
Okay.
How much post-processing did you have to do, Mario?
A whole night's worth. It was painful to get this one.
Wow.
Yeah. That dynamic range, I'm sure, is huge on that.
Yeah, very huge. So this is another thing when you get into astrophotography. Yes, there's a technology and there's a lot of methodology, but there's art, because you're actually choosing what you want to bring out. Even with the science of the James Webb images, the scientists are actually making decisions as to what they want to show. And so I regard that sort of as an art.
Yeah, I 100% think it is.
Yeah.
Some of those Webb telescope images look like Mandelbrot sets where you go in and in and in, and it's more detail everywhere you go.
Yeah.
Yeah, 100% agree.
It was incredible stuff, especially the voids. I mean,
yeah,
we're looking at only 5% of what they think is out there. So we're still back in the Galileo telescope thing. It's like, I don't know, I can't tell what's going on. Yeah, it really is amazing.
So I want to thank Tony, and I was very happy to see his folks briefly. I think they've gone off to celebrate with ice cream.
I think that they messaged that they were going home. So
Sorry, I was late. I got home late.
Well, you know so much about this as well. So I'm going to call it an evening. Thank you all for hanging in there and participating. And I look forward to seeing you all again a month from now.
Thank you very much.
Okay.
Pleasure seeing you all.
Thank you, everyone.
Take care.
Bye.
Thank you.
Bye, Tony.